Hello everyone. So today we will start our chapter 5. So that's object oriented software engineering. So we will do it in design phase. I hope you remember what's the design phase is. It's actually a second phase of a software engineering life cycle. So after we are done with our requirement engineering, we already know what our system will do, right? So now in design phase, we will not do the actual programming or implementation, but we will model our system in a way so that we know how we should implement our system. So that's the task of design phase. It specifies the structure of your system, like how you will implement your structure without actually writing the complete code or complete implementation. So it's actually defining from what the system will do to how the system will do it. So in requirement engineering phase, you already know what your system will be capable to do, and in design phase you will transform from what to how the system will do it. So now as we are talking about object oriented design, so it will be related with objects, classes, those things, right? So in our today's lecture we will focus only on class diagram and object diagram. So that's why I have kept them limited to objects and classes today. But as we proceed to other diagrams, then we will enrich this section later. Okay, so when we are thinking about class diagram, so in the design phase, what you will think that what classes you need to implement the system, right? What classes you will need to implement a system that meets our requirements. So that means you will keep a list of classes, and then what fields or methods you will need to implement each class. So you will fix those things in your design phase, like your list of classes, the attributes or methods of the classes, and the interaction between classes. So if we are thinking of using a class diagram, then we will fix those stuff in design phase. So before jumping to the actual implementation of those class diagrams, or how we should depict those class diagrams, I just want to give a little bit overview of classes and objects. I know you guys already have learned about these stuff in CS 110, right? You already have completed a C++ course. So in that course, of course you have learned about class, object, and inheritance, generalization, polymorphism, all those stuff. So I will not give details, I'll just touch those concepts. So the first one, object. So what's an object? An object is actually a real world element in an object oriented environment that may have a physical or a conceptual existence. So now when I'm talking about physical existence, it means that your object could be a customer or a student, an employee, a car, so anything. This has a physical existence, so you can think it as an object. And also it could have conceptual existence, like a project, that's a conceptual existence, but that's also a object. Or you can think a process as an object, or a sub project as an object. So those have conceptual existence, those are also accepted as object. So each object has identity, a state, and a behavior. So what is an identity? Identity actually distinguishes it from other objects in the system. Like every student has a ID, right? So that's why using those ID we can distinguish one student from other. So that's an identity. And the next one is state. State actually determines the characteristic properties of an object, as well as the values of the properties that the object holds. And behavior represents externally visible activities performed by an object in terms of change in its state. So these are object. So object actually composed of an identity, a state, and a behavior. And the next one is class. Class represents a collection of objects having same characteristic properties that exhibit common behavior. So common behavior is actually an important thing in class. You can see here that the concept of class and object are actually linked with each other. A class represents a collection of objects that has common behavior. An object is an instance of a class, so they are actually interlinked with each other. A class consists of a set of attributes and a set of operations. Let's give an example, then you will have better idea. Suppose you want to represent a geometrical figure circle in two-dimensional space. Okay, so you will create a class, a simple class that is circle, and the attributes of that class will be x coordinate of the center, y coordinate of the center, and the radius of the circle. So these are the attributes. The x coordinate of the center, y coordinate of the center, and the radius of the circle are attribute of the class. And you will have a set of operations, like you can calculate the area of the circle, then it will be a operation. So you can also have other operations like scale. You can change the radius of the circle using that scale operation. So these are set of functions or methods. Now you can create an object of your class. Suppose you can create circle 1, that's an object of your class, and then you can assign values of the x coordinate, y coordinate, and the radius to the object. Okay, so you can assign values of x coordinate. Suppose you have assigned it 2, and y coordinate suppose you have assigned 3, and the radius suppose you have assigned 4, and all these will depict a state of that object. Okay, and if you change, suppose you have used the scale function with a scaling factor of 2, then your radius will be 8. So the scale function actually brings a change in the state of the circle. So the object has exhibited a certain behavior. So now you understand what is behavior, state, a set of attributes, and set of operations. So I have explained this already. So now move to the most important concept of this chapter. We will actually start this UML in this chapter, in this entire chapter. So UML is actually a short form of Unified Modeling Language, or you can also say it's union of all modeling languages. It's a standardized modeling language, consists of an integrated set of diagrams. The UML mostly actually uses graphical notations to express the design of a software project, and it helps project teams to communicate, explore potential designs, and also validate the architecture design of the software. It was developed in 1990s as an amalgamation of several techniques like object-oriented analysis and design technique, object modeling technique, and object-oriented software engineering technique. So it's actually a combination or union of all modeling languages. So UML has actually 13 diagrams. I will show you the diagrams in the next slide. So the most used diagram is actually class diagram. So in today's lecture we will cover class diagram. So 75% of the software engineers uses class diagram mostly, and also use case diagram is also popular, and the other diagrams are not so popular, but we still have 13 diagrams and we will cover most of the diagrams. So these are the diagrams: class diagram, component diagram, object diagram, lots of diagram here. So when we look at this diagram, the first thing we notice that there are lots of different diagrams to get used to it, right? And the reason behind having a lot of different diagram is that you could have different viewpoints for your software, right? Like in your software team, you will have analysts, you will have coders, testers, QAs, the customer, technical authors. All of these people will look differently in your software. All of these people are interested in different aspects of the system, and each of them require a different level of details, right? Not everyone will require same details. Coders will need different details, analysis, designers, customers, they need different kinds of details. So that's why the UML attempts to provide a language so expressive that all stakeholders can benefit from at least one UML diagram. So that's why UML is important. So now the first diagram we will look at is UML class diagram. UML class diagram, it actually models the static view of a system. It comprises of many classes, interfaces, and collaboration of a system and the relationship between them. So you will identify the classes, you will identify the relationship between different classes or interfaces. So that's your UML class diagram. So here, details of how the classes interact with each other is not given here. You will not give details. You will just give the connections between them and the relationships between them, but not details like how they are interconnected, or not algorithmic details. Those are not included in the UML class diagram. You will list the different classes of your system, you will give them name, you will give the attributes of those classes, and you will give the relationship between different classes. So that's UML class diagram. So now we will give some notations how you will draw a class diagram. So the first notation is how you will define class. So a class is actually represented by a rectangle having three sections. It has three sections. The top section, it actually contains the name of the class. So you will assign a class name here, and if your class is an abstract class, then the class name will be in italics. And in the middle section will contain the class attributes. Well, like in the previous example I told you, suppose you have created a class, so for the class circle, so circle is the name of the class, and the x coordinator of the center, y coordinator of the center, and the radius is the attribute of the class. And if you give them some functions like find area, scale, find circumference, those will be the set of functions or set of methods or operations in your class. So that's how you will represent a class. Now there is another thing, that is visibility. You know how we define the visibility of a class. So it could be public, it could be private and protected. The functions that you have defined in your class will could be public. So public member is actually visible from anywhere in the system, and for representing public you will add a symbol plus, and for representing private you will add a symbol minus. Private member is visible only from within the class, it cannot be accessed from outside the class. And you can also define your set of functions as protected. So the protected member is visible from within the class and from the subclasses inherited from this class. So you already know what inheritance is. So if you want to give them the protected visibility, you will add the hash function. You will prefix it with the hash function, then it will represent protected. So in the previous figure you can see we assume that x coordinate and y coordinate are private data, and the radius is a protected data, and the member functions are public here. So that's the visibility. So this is the notation to represent a class. Now these are the notations for relations. If you want to represent dependency relation, it will be dashed line. For association or link, it will be just a line. For inheritance, it will be a directed line. So these are the different notations for representing relations. So for relations between classes, the concept of generalization, association, dependency, aggregation, composition, these are important to understand the relation between classes. So generalization and specialization, these are two terms. I hope you are already familiar with these two terms, but still I'm just giving a brief idea. Generalization and specialization actually represent a hierarchy relation between classes where subclasses inherit from superclasses. Okay, so this is a hierarchy relation, and it's related with inheritance. So the subclasses of a class will inherit some attributes from the superclass. So this is a generalization relationship. We can also say the common characteristic of a class are combined to form a class in a higher level of hierarchy. Okay, so suppose the subclasses are combined to form a generalized superclass. It represents a kind of is a kind relationship. Let's say car is a kind of land vehicle. So here I'm showing is a kind of relationship. It's a generalization. Or I can say ship is a kind of water vehicle. So it's is a kind of relationship. So here we are generalizing it. So that's generalization. And specialization is actually a reverse process of generalization. Here the distinguishing features of groups of objects are used to form specialized classes from existing classes. It can be said that the subclasses are the specialized version of the superclass. So that's generalization and specialization. And association actually depicts the relationship between objects of one or more classes. Okay, so if the two classes in a model need to communicate with each other, there must be a link between them, and that can be represented by association, or you can simply think it as a connector. Okay, so association can be represented by a line between these classes with an arrow indicating the navigation direction. So you need just a line with an indication. So that's association. So now we will show how we can show the generalization relationship with different classes. So I already told you that the generalization is actually a hierarchy. So it's top-down approach. We will draw it using top-down approach, and we will use arrows to point upward to parent. So that's how you will draw it, and you can use line or arrow style to indicate the parent. Now here, if your parent is a class, then you will use a solid line with black arrow. But if your parent is the abstract class, then you will use solid line with white arrow. And if your parent is an interface, then you will use dashed line with white arrow. So here is an example of generalization within classes. So you can see the rectangle is a class, and the parent here we are assuming that it's an abstract class. So if we use color, you will see that it's a line with white arrow. So this is a parent-children relationship, and here the parent of rectangular shape is an interface. We are assuming it's an interface, so that's why we have used the dashed line here. So this is a generalized how you will show generalization relationship in your class diagram. So the next one is association. I have already explained you what association is. It's a link between different classes. So for representing association, you will need multiplicity, you will need a name, and you will need a direction. Okay, so here multiplicity, it could be one-to-one relation, it could be one-to-many relation, it could be many-to-many relation. So if you have a one-to-one relationship between two classes, then you will show it using 1-to-1 exactly. If you have one-to-many relationship, you will write one in one side and star in other side. If you have many-to-many relationship, you will just represent it with star. Okay, and you can also define it like 3 or more relationship. So that's why you will put 3 and then a star. So this is your multiplicity, like what's the cardinality of their relationship, and you will need a name for the relationship, and you will need a direction for the relationship. That's your association. That's how you will represent the association relationship. So this is the multiplicity. I already explained it. So we have some more real association types. So aggregation, composition, this is also association types. So aggregation and composition are actually subsets of association, meaning that they are specific cases of association. So aggregation is referred as a part of or has a relationship with the ability to navigate from the whole to its parts. Okay, suppose if I say a car has a motor, okay, or a car has an engine, so these are actually aggregation. So car is the whole object or the aggregated object, and the motor is a part of the car. These are aggregation and composition. So both aggregation and composition object of one class owns object of another class. So both in aggregation and composition, we actually owns objects from another class. Okay, but there is a difference. The aggregation is actually implying a relationship where the child can exist independently of the parent. For example, if you say that the car, that's a parent here, and an engine, that's a child, and you are showing the relationship between them. So now if you delete the car, and you still can think that the engine still exists, so that's an aggregation. It defines a relationship where the child can exist independently of the parent, so that will be aggregation. And in composition, it implies that the relationship is kind of where the child cannot exist independent of the parent. So if you think book as a parent and the page as a child, so page don't exist separate to a book, right? So that's why it's a composition relationship. It's entirely made of relationship, and in aggregation it's a part of relationship. And we have another one, that's dependency. The dependency is a directed relationship which is used to show that some UML element or set of elements requires or needs or depends on other model elements for specification or implementation. So that's dependency, it's dependent. Okay, so here it's symbolized by dotted line. So we have added 3 examples here. Aggregation is actually symbolized by a clear white diamond, composition is symbolized by a black diamond, and dependency is symbolized by dotted line. So these are 3 kinds of association that will be used in class diagrams. So here is an example of a class diagram. We have already learned about the notations, how we will use the class, what should we use to represent the class diagram. So now we will see a total picture of a class diagram. we are considering a simplified banking system here. So what a bank usually have, it usually has so many branches. So you will consider some branches. In each zone, one branch is considered as the zonal head office that supervises the other branches in that zone, and each branch can have multiple accounts and loans, right? An account could be either saving account or it could be either current account, and a customer may open both a saving account and a current account. Okay, but here is a catch: a customer must not have more than one saving account or current account. The customer will have only one saving account. He could have both, one saving account, one current account, but not more than one saving account and one current account. And a customer may also procure loans from the bank, of course. So these are the total system that we are thinking, we are considering. Okay, so this figure is actually showing the class diagram of the system. So what will be the classes in the banking system? We already have discussed that we will have a bank. Okay, that's a class. We will have different branches, so branch will be a class. We could have different accounts, so account will be a class. And we could have saving account, we could have current account, so those are different classes. Then a customer can also take loan, so loan will be a class, and the customer will be a different class. So we need customer classes to store their IDs, their informations, right? So that's why we need another class, customer. So in total we have used 7 class here. Okay, you can have more if you want. So now you have the list of classes in your hand. So what you will do, you will draw the classes, and you will identify what's the function of each classes, right? What's the function of a bank, what's the function or functional work for the branch, what will be the functions for current account, what would be the functions for savings account. So you will identify the functions and you will write it in the class. So the next thing is you have to identify relationship between the different classes. So a bank has a number of branches. So here you can see it contains a has a relationship. So it's a composition. So we have drawn it using a black diamond, and also it's a one-to-many relation. One bank could have more than one branches. Okay, could have many branches, so it's a one-to-many relationship. And a branch with it can have a role for zonal head office, and that head office will supervise other branches. So it's an association here, and it's a one to many relationship. One branch, one head office will supervise other branches. Okay, so it's a unary relationship and it's a one to many relationship. And a branch, it has a number of accounts. Okay, so it's an aggregation here. So why it's an aggregation? Because the accounts can hold without even the parent. So that's an aggregation relationship, and we are showing it with white diamond. Okay, so again it's a one to many relationship here. And a class account, it has two subclasses, that's current account and saving account. And current account and saving account both actually inherits from the account class, right? From the class account. So the class account has two subclasses, that's savings account and current account. They inherit the attributes from the class account. So a customer can have one current account, so that's why it's an association, it's a one-to-one relationship. And a customer can have one saving account, so that's why it's an one-to-one relationship. And a branch has a number of loans. Okay, so that's why it's an aggregation relationship, and also it's a one to many relationship. and a customer may take many loans. There is no restriction, right? So that's why it's an association and it's a one to many relationship. So these are the relationship, and this is the class diagram of a simplified banking system.